Good afternoon, everybody, and thank you so much for joining today. As Kenneth said, we are taking the Q&A via the EESSI Slack, so please join the channel if you haven't already. And a reminder that this is the first session of a series of webinars we are doing for the next 5 Mondays. And today we are in the Introduction to EESSI one. I assume that if you are here, it's because you registered already, but you can do it for the next sessions too in the QR code here. And these slides are uploaded, so you can take a look after. And without further ado, so what if I told you that you have no longer to install a broad range of scientific software from scratch on every laptop, HPC cluster, or cloud instance that you use or maintain without compromising on performance? Well, EESSI, the European Environment for Scientific Software Installations, can help you with that. So welcome to the first session, Introduction to EESSI. And today I'm joined with Richard and Thomas from the University of Bergen, Kenneth from UGent, and I am Elena from IT Now. Richard and me will be speaking, and Thomas and Kenneth will be helping with the Q&A and moderating the session. So let's go. So why are we doing this? Sure that you know that scientific software is already a massive ecosystem and it just keeps growing from bioinformatics, physics, AI, earth sciences, engineering, blah, 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 blah. And to top it, scientists have to run their codes in a variety of systems. Lately, there's a tendency for going to the cloud for more flexibility, but on the on-prem clusters, there are quite heterogeneous architectures with all the Intel, AMD, ARM, RISC-V, hopefully soon, and so on. And from a bunch of user supports and sysadmins in the room, we can guarantee that hands are always limited compared to the amount of software installation requests that we receive in HPC centers. And this is not only a problem in academia, but in industry too. I'm the only one here coming from a private company, and we have to keep a lot of app stacks for different clients. So this is a huge problem everywhere. So the major goal of EESSI is to provide a truly uniform software stack. This means finding the exact same software everywhere you have EESSI available and without sacrificing performance, because remember, we do high performance computing. And assessing this problem helps significantly to avoid duplicate work for all support teams and sysadmins all over the world. Sure, you might have heard of EESSI Build or SPAC. Well, with this kind of tools, users work providing recipes to each repository, but with EESSI, we rethink on how we share software entirely. We're talking about distributing binaries in a shared software stack, not only the steps to build that software. So it's a complete step further in software sharing. With this, we also support facilitating HPC training and the development of scientific software, but that's for later in the presentation. So as I said, we do high performance computing, so it's important for us to keep the P in HPC. And as I explained, EESSI is about sharing binaries, and there's a huge effort behind to optimize these binaries for the system they will run on. Take a look at these builds of Gramax. These are the ones taken from the distribution repositories, and these are the ones compiled for the architecture they will run on. You can see there's a huge speed up. So demo time. I will show you a bit about how that I'm not lying to you. So this is my laptop. As you can see, it's a normal Ubuntu, nothing special. And if I do a LS CPU, you can see it's a normal Intel, nothing fancy here. So I have Elmod installed, but I don't have any software installed in my app stack. So what I'm going to do now is EESSI. It might be installed, but it's not activated. So I'm going to activate it. And this is done with sourcing this script. We will get into how it's installed and how you can do this later on, but this is just to show you that I'm not lying. So I'm sourcing this script. And now it is being activated. And as you can see, it detected the architecture of my laptop. So it was an X8864, it's an Intel, and a Haswell. Also, my laptop doesn't have any GPU, so it didn't detect any. And if I now do a module avail, I have this whole AppStack available for me. And as you can see also here, it goes to fetch the modules of that match my laptop architecture. So I can run software that's optimized for my laptop. And as you can see, there's a very, 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 very big AppStack here available for me. And this is only the on top software. There are also the extensions. All of these are like R packages, Python packages, Perl, yada, yada, yada. And so this not only works for Ubuntu, this works for a lot, well, every architecture and every OS basically. So what I'm going to show you now is I'm going to do the same for a different system. So this is a test environment we have in my company. And I'm going to do the exact same. As you see, it's different. This is Oracle Linux. And if I do an LS CPU, it's also an Intel, but it's a different processor. So if I now do the same sourcing, EESSI gets activated. And as you can see, it's slightly different because it's the same architecture and an Intel, but this one is a Skylake AVX 512. And if I now do module avail, here I can see how. So notice the difference. This one is for, again, the architecture of this system, and this one was for, well, it's too much above, but it was for my laptop. Again, we will show you how to install and do this in the next demo, but for the moment, this is just for you to show that everything works everywhere. So following up, this is the same I showed you, just a backup slide. And you've seen the magic, so now let's get into how it works. And the key points are that these binaries are streamed on demand via CVMFS, and we'll get into that shortly too. And this is built to be independent of the host operating system thanks to the compatibility layer, as you've seen. And the binaries are optimized for the specific CPU generations and GPU types, which are detected in the initialization script, as you've seen too. And now let's zoom a bit into these layers. So I will explain these layers also separately, but this slide is for you to visualize it first. So from bottom to top, we have our machine. This is the iron, as we call it, with its particular architecture. And this machine has an operating system installed. You've seen that in the case of my laptop, it's a normal Ubuntu running on Intel, nothing fancy. Then we have the host operating system provides the drivers for the network and GPU. Also resource managers like Slurm. And on top of it, we have the file system layer. This is where the files of the software stack are distributed via CERN BMFS. And on top of it, we have the compatibility layer that runs on Gen 2. And yes, it's technically an operating system too, but we use a very minimal installation located in a particular prefix. So this way we can compile the app stack with all apps pointing to the same glibcs and other system libraries. Again, I will show that in deep later. And finally, on top of it, we have the software layer. This is different from the file system layer, as the file system layer is the infrastructure to distribute the software, and the software layer is the software itself. And I hope that's clear. Here we have EasyBuild and LMod helping us to build the software, and ArcSpec to detect the architecture underneath and cross-compile accordingly. And all of this is tested via Reframe. So now let's get into details. The file system layer relies entirely on CERN BMFS, and as the name suggests, it's an open source project developed by the CERN itself. So the way it works is there's a central server we call the Stratum 0. This one is the only writable one, and it hosts all the data, absolutely centralized, and there's only one. And surrounding it, there's a constellation of mirrors we call Stratum 1s. They replicate the data from the Stratum 0, so it makes the whole infrastructure more robust. But those are read-only. And finally, we have proxies to cache the data from the Stratum 1s. This usually, where if somebody wants to access the repo, these proxies are the ones being poked. So this way we leverage the accesses and the reads to the Stratum 1s. And any machine with CERN-BMFS installed can access this, no matter if it's a laptop, an HPC cluster, a cloud, etc. So as you see, it's the same, exact same data anywhere. And how is it implemented in EESSI? Well, our Stratum 0 is in the University of Groningen in the Netherlands, and we have mirrors, one in AWS and one with Azure, one in Europe and the other one in the US East Zone. And we have a sync server, also in AWS. And then we have some proxies. If you want to know more about CERN-BMFS, reminder that next Monday's webinar is the introduction to it, and I hope to see you there too. And so now going a bit up in the layers about the compatibility one, this is where the things get a bit tricky. So as I explained, the compatibility layer consists of a Gen 2 minimal distribution installed in as a prefix. And well, it's under a directory that we'll check as soon as I finish this the slide. So all typically system libraries are installed here, and this ensures that for all of the abstract, there's a uniform glibc. And again, these are libraries, not drivers. Drivers are provided by the host. So this acts like a container, but without being a container. And it makes everything homogeneous to work with, because every operating system has their own set of libraries in different locations and so on. And these only target a supported processor family, as you can see. And there are also different versions of it. And you can find them under this location in EESSI. And I'm not going to share with you again. So if I now go to defense, versions 2023. This is the compat layer. And if I now go for my supported architecture, and this is what typically a Gen 2 prefix installation looks like. So this simulates an entire operating system, but in a very minimal version. So we have the binaries, the libraries, and the lib64. But if I now go to the user, well, here you see that these are the typical system libraries. So every app that we compile through EESSI, it's pointing here. So everything is homogeneous. We don't have any glibc problems. Everything is fine. Also, you can check this by yourself in case you want to take a look on how it looks. So moving on. The software layer is the one providing the software itself. This is the binaries of applications, libraries generated by them, dependencies they might need, Python, packages, R, Perl, and so on. Again, these binaries are optimized for the architecture they will run on. And we have a very big infrastructure that does multiple compilations for each architecture using the corresponding flags in each one of them to ensure that the binaries are optimized. And we also support NVIDIA GPUs, and you can find them under the accelerated directory. We do the builds using EasyBuild recipes and environment module files are accessed using LMOD. And as you've seen already, ArcDetect is the library responsible for choosing the best subdirectory in the repo with the software suitable for the host it will run on. And what architectures we do support? Well, the generic ones like x86-64, also specifics for Intel like Skylake, Ice Lake, and all the lakes. Also AMD's Zen 2, 3, and 4, and the ARM64 CPUs. Also, we have a RISC-V repo, which is growing every day, but it's still a work in progress. And for accelerators, we have these combinations. But it's basically the Zens, AMD ones with different NVIDIA GPUs. And we do not only support different architectures, but also different network technologies. like InfiniBand. And the goal is to support the architectures for the current and future Euro HPC systems. And speaking of which, we are doing a good job so far because EESSI is available and ready to use natively on major Euro HPC systems like Vega, Carolina, and Deucalion. And for Mare Nostrum 5, it's quite a different setup, but it's definitely available there. And there are other ways to access EESSI, and in case you don't have CERN BMFS available, you can use this tool called CBMFS exec, and you can check the blog post on how it works linked there. Again, these slides are posted, so you can look at it at your own pace. And Meloxina and Lumi is a work in progress. And for Jupiter, the first European exascale, we have already everything in place for when the machine is in production, so sure it will be available there too. And it's also available in other European systems. Here you can see a list of some. Here you can see the list of some of them, but you have a full view of where is it available in this webpage. So, hey, we have the same software stack applications installing EESSI, and these are streamed to the Euro HPC systems and beyond. So, researchers that run their codes on different systems, it will be much easier for them to, just load the exact same module everywhere. And about NVIDIA GPU support, it's in place, but it's been a long journey. First of all, because technically the licensing doesn't allow us to redistribute the full CUDA installation, only the runtime libraries. And especially because beforehand, we don't know where the GPU libraries are located in the host, as every system is just different. So we have a couple of scripts to solve these problems, but I don't want to get too technical. You have this in our repository, so you can also check it by yourself. And these are, we have already a good amount of GPU software available and more to come soon. And it's important to mention that even though EESSI support is funded through the multi-scale COE, this is a community effort and everyone can collaborate. And right now we have about 960 software installations available per CPU target and almost 500 different software packages. And these are growing. And we also have major and famous scientific software as Espresso, GramMax, LAMPS, OpenFlow, PyTorch, blah, 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 blah. And then we also have Python bundles, R bundles, bioconductor bundles, Perl bundles, and so on. And you can check the available software in this webpage. And the aim is to use recent toolchains to compile everything. And right now we are focusing on the FOSS 2023 AMD. So to sum it a bit, the current production repository for EESSI is software.easy.io. That's the one being updated constantly. And in the GitHub, you can find everything. All the layers separately have their own repo. Then you have the configuration, orchestration files, documentation, supporting scripts, stack files, and so on. So again, everything open source. You can take a look if you want to. And these are the targeted microarchitectures. We have the generic ones, then the specifics for Intel, AMD, and ARC24. And the NVIDIA GPU support is in place, and we are currently working installing more and more software. There's a lot of effort right now into pushing Grace Hopper software for the new Jupiter. And of course, a huge thank you to Azure and AWS to support the project with the cloud credits to host infrastructure. And now I will give the floor to Richard.
Thank you, Elena. Hi, everyone. My name is Richard Topusyan, and I've been contributing to the EESSI project for around 2 years. I'm glad to be here today to share information about EESSI, along with some of its use cases. Now that we have an understanding of what EESSI is and how it works, it's time to get to know how to access EESSI. For a single system, a native installation and configuration of the CERN VMFS client is typically sufficient to access EESSI. However, for a set of local clients on an HPC cluster or set of workstations where greater reliability and improved software startup performance are critical, this basic setup may not be enough. In such cases, it is recommended to deploy a private CERN VMFS Stratum 1 or what is called a mirror server in your local network, which will make a full copy of the EESSI repositories on the Stratum 0 or the central server, along with one or more Squid proxies close to your clients, which will be used to cache the content that was recently accessed. This setup helps offload traffic from the Stratum 1 server or servers and reduces the latency for your clients. It also enhances the reliability of the access to EESSI. For more information concerning CERN VMFS and best practices, you can check the link for CVMFS tutorial HPC best practices under multiXscale.github.io and attend next Monday's session, which you can find by scanning the QR code shown on the screen. From a user perspective, where a CERN VMFS client is available on the system, accessing EESSI is a straightforward process. By sourcing the provided bash script, a user can initialize the EESSI environment and access its software modules. The software on demand will first be searched within the CVMFS client cache on the client system. If it is not available, it will be searched within the Mirror 1 server or the Stratum 1 and then delivered to the client cache and so to the user. It is good to mention that the Stratum 1 server is periodically synced with the central server or the Stratum 0, where the EESSI scientific software is added. So, EESSI offers on-demand access to scientific software, much like how streaming services deliver music or TV series. You might recognize this slide from earlier in the presentation. We brought it back intentionally to briefly revisit how the different layers of EESSI are structured and how they interact. This is helpful before we start with the live demo. At the bottom, we have the host operating system that can be any Linux distribution. It provides drivers for the hardware resources. It can also provide a resource manager such as Slurm. On top, we have the file system layer, which manages the distribution of the software stack. On top, we have the compatibility layer, which levels the ground across Linux distributions for EESSI. For x86-64 CPU microarchitectures on one hand, and for ARM CPU microarchitectures on the other. And finally, we have the software layer where optimized application and dependencies for specific CPU generations and GPU types are available. The native installation of CERN VFS is a simpler process for RHEL-based distributions like CentOS, Rocky Linux, Alma Linux, Fedora, etc. Basically, it consists of 5 steps. First, to add the CVMFS repo to the YUM repository on the system. Then to install CVMFS. Then add a configuration file on the system. Specify a client cache limit to that configuration file. And finally, make sure that EESSI CERN VMFS repository is accessible through running sudo cvmfs config setup. You can find more information about this through the link provided below. And also, it is good to mention that this procedure requires sudo privileges. Now we will run a live demo. On the first run, we will be using a fresh VM, basically on AWS. Basically, it is an AMD CPU. There we will be installing SermVMFS, which requires root access, and applying the steps mentioned earlier. This can be used on laptops, virtual machines, or any system with administrative privileges. After that, we will come to another scenario where no administrative privileges are required. As you can see, this is a VM on AWS. Also, I will try to show you the CPU microarchitecture. So as we can see, it is an AMD CPU microarchitecture. Basically, it resembles the Zen 3. And I will also show you that there is no CVMFS installed. So if I try to do which CVMFS config, I will see that CMFS config is not available. And also if I do module -- version, I can see that even Lmode is not available. So what I want to do now is just copy paste the steps I mentioned earlier on the system and install CMFS client. So first, I will add the CVMFS repository to the current yum repository on the system. Next, I will be installing CVMFS. It's almost there. And all what is left is to add a configuration file. Add a clash limit to the CVMFS client. And here we can see that I am adding a limit of 10 gigabytes. And finally, just execute sudo cvmfs config setup. And after this, just to make sure that I can see the directories under /cvmfs software.easy.io, I can run ls/cvmfs software.easy.io. And now I can see that the directories under /cvmfs software.easy.io are accessible. So all what is left to do is just source the CVMFS software versions init path script that is provided by EESSI to get access to the software stack that is available through EESSI. Here we can see that first it tried to detect the CPU microarchitecture that I showed you earlier, which is a Zen 3, AMD Zen 3 CPU microarchitecture. It then tries to find if there are any accelerators on the system. Here we don't have any. And then it offers me the software stack that is best optimized for my CPU microarchitecture. And as we can see, it is under the Zen 3. So now, if I simply try to do module avail GrowMax, I can see that I am offered different versions of GrowMax. And keep in mind that earlier I showed you that there was no even Lmode available on the system. To go further and do a demo, I will clone the GitHub repository for EESSI. So I will git clone the demo repository for EESSI. I will access the repository, and there I can see some software which the demo offers small examples for various scientific software applications included in the EESSI software repo. So now if I try to run GrowMax, I will go into GrowMax and simply /run.sh. I can see now it is first trying to load the GrowMax module software from under the Zen 3 CPU microarchitecture. It first checks the client cache, and if it's not available, as the case now, because it's the first run, it will try to fetch it from the Stratum 1 server. And after that, we can see that it already has started the simulation. And we can see it's using 1 MPI and 8 OpenMP threads. And now the simulation is over. So as simply as sourcing the shell script, we get access to a full software stack that is optimized for our CPU microarchitecture. I will run another test using another software. So I will go back and go to TensorFlow, and I will try to run a simulation using TensorFlow. Keep in mind, there is around 1 gig of data to be fetched from the Stratum 1 server on the first run, and almost 3,500 files. So now that it's done, we can see that it has already started running. And there you go. The run is over. What I will do now is I will execute the same script again to show you that when the software is available in the client cache, the process is much faster instead of fetching it from the Stratum 1 server. So if I execute the same command again, I can see that it will first try to fetch the software from the client cache, and since it found it, it directly starts running the simulation. And there you go, TensorFlow simulation is done. So this is the first approach. I will now leave the VM. And for the second approach, I will further explain that for the second approach, I will be using an ARM-based CPU microarchitecture on another virtual machine in AWS, but this time I will not be requiring any root access. Basically, all I need is an obtainer or singularity with specific versions and Git. This is a specific use case, for example, on HPC systems where obtainer or singularity is available, but no native installation of CERN VMFS is yet there. So now I will go back and use another VM. This is another VM on AWS. I will do ls CPU to show you that this is an ARM-based CPU microarchitecture, specifically Neoverse v1. And all I need now is to use the Git and clone the GitHub EESSI software layer repository. And now if I access software layer, and since I have already made sure that obtainer or singularity is installed, but I can further check that using singularity -- version, for example. And now I can, all that I need to do is execute the EESSI_container shell script. As you can see, it will first download an image, container image. It will put it in the temp. Here, it's also good to mention that you can reuse this image. So on the next run, if you want to use the already downloaded image, you can use it through the -- resume option. And you can check other options using the -- help after executing the EESSI_container shell script. There are several options that can be useful on specific cases that you might run into. So now that the image is there, I am offered access to /cvmfs. So if I do a df, I can see that cvmfs is now accessible. I will repeat exactly the same steps which I have done earlier. So I will do ls/cvmfs software.easy.io, and I can see that I have access to the folders underneath. So all what is left is to source/cvmfs software versions init bash. And exactly as before, this script is enough to auto-detect my CPU microarchitecture. As I can see here, it has detected the Neoverse V1 ARM-based CPU microarchitecture. It also searched if there are any accelerators, which I don't have any now, and it offered me the software stack that is best optimized for my CPU microarchitecture. And now I will also do an module avail GrowMax. And here you can see exactly the same three versions which we saw earlier, but now we see them for the best optimized software stack for my CPU microarchitecture, that is the Neoverse V1. And I will repeat exactly what I've done earlier. I will git clone the easy demo repository from GitHub, and I will go into that and also GrowMax, and I will execute the same shell script that I've did earlier to show you that very simply I'm getting access to a software stack optimized for my CPU microarchitecture. And there you can see that it already has started the simulation for GrowMax. And again, as explained earlier, it fetches the software from the Stratum one because on the first run, it is not yet available in the client cache. So now it's almost there and the simulation is done. I will also run for the same thing for TensorFlow that show you that it is exactly the same, just a different stack is provided based on my CPU microarchitecture. So if I run this now, it will again try to fetch the files, which are almost 3,500 files with around 1 gigabyte of data required to run this simulation. And there we go. So in these two cases, we have seen easy software stack running on two different CPU microarchitectures using two different approaches. One when we have pseudo privileges and one with no pseudo privileges. Now I will exit this and go back to the presentations. Here is another example of how to run easy within a Slurm job script. So all is required is a single line where we source the cvmfs software.easy.io/version/init bash, that is the bash script provided by Easy. It is enough to detect the CPU microarchitecture on the system or on the node that I'm willing to run the software on. Some of you might already be wondering, like, what if the software you need is not provided by Easy yet? In this scenario, we have two approaches again. First, we can try to build on top of Easy using Easy Build. In this case, you load the Easy environment and then you load the Easy Extend module, which automatically will load the Easy Build module. And then you are given the option of building the software with using three approaches, either to the user only, or project-based, or even for the whole site. This is a use case if you're using Easy on an HPC system, for example. And we build the software on Easy using the same approach, but instead we build it in /cvmfs instead of building the software locally. For more information about this, you can find it through the link provided under easy.io/docs, and you can also attend the session on the 19th of May and on the 2nd of June. There you can get more information about how to use EasyBuild and how to build on top of Easy. The second approach is, so in the first one, you basically build the software locally only for your system. But how about like contributing to the Easy software stack and make the software available for others? In this approach, you can contribute to the Easy software stack through following the documentation under easy.io/docs, adding software, where you can find the contribution policy, which is a guideline for adding software to Easy. To add software to Easy, first, the contributor makes a pull request to the GitHub repository on Easy software layer. Then reviewers from Easy will check this pull request and make sure that it is compliant with the contribution policy that I mentioned earlier. Then jobs will be submitted to bots on different systems, which build the software on different nodes with different CPU microarchitectures to make sure that the software is optimized for a specific CPU microarchitecture. And as we can see here, Easy already provides software stacks specified, optimized for different x86 and ARM CPU microarchitectures. For x86-64, software stack exists for AMD Zen 2, AMD Zen 3, and AMD Zen 4. For Intel Haswell, Intel Skylake, and Intel Sapphire Rapids. And there is also the generic, which is the default in case you are on an x86-64 CPU microarchitecture that is not yet supported by Easy. And also there is a work in progress for Intel Ice Lake and Intel Cascade Lake. For ARM-based CPU microarchitectures, Easy already supports Neoverse N1, Neoverse V1, and the NVIDIA Grace, which is found on Jupyter. There is also the default generic, and there is a work in progress for the A64FX that is found on Deucalion. After the software is built, some tests from Easy software stack are run. After that, the software that is built is compressed into a tarball and signed. Then the tarball is transferred to an S3 bucket. A cron job will pick up those tarballs and transfer them to the Stratum 0 server or the central server. There, the signature will be verified, and an pull request will be opened to the Easy Staging GitHub repository. There again, reviewers will make sure that the pull request is valid, and after approval, the software that is built will be deployed in the Easy software stack, and it will be accessible by users. You can find more information and the description about this under easy.io/docs/software layer adding software. In Easy, we don't just build the software, we make sure through tests that the software that we build is valid. So we run two types of tests. First, the smoke test, which are the sanity check commands that are run by EasyBuild to check that the software is not horribly broken while using EasyBuild. Another type of test we run is the regression testing via the Easy Test Suite. Those are a collection of portable tests for software available in Easy. They are run on a single node when the software that will be newly added in the software stack, and those tests are run before deploying the software. They are run periodically on multiple different systems, can also be used for other software stacks that are built using EasyBuild. And it's also good to mention that periodic runs of Easy Test Suite can help to catch a performance regression, for example, after a system upgrade or a change in the configuration. Through the regression tests, we were able to identify a bug in the GROMACS version. Then the bug was reported and an issue was opened on GROMACS, where GROMACS developers followed up the issue and were able to resolve the case and made a patch so the bug was fixed in a later version of GROMACS, in specifically GROMACS 2024.3. For more information about this, you can check the links available on the screen. So when we run the Easy Test Suite, we get some results. There, Easy also provides a dashboard to make use of those results. So the Easy dashboard offers a centralized interface for visualizing results generated by the Easy Test Suite. It supports a range of use cases, including performance analysis on individual systems, allowing users to monitor trends and detect anomalies over time, cross-system performance comparison, enabling evaluation of how the Easy software stack behaves across different hardware and environments, system monitoring, providing insight into the health and stability of platforms where Easy is deployed, and finally, regression source identification, helping distinguish whether the observed issue or issues are a result for a recent change in a system hardware or configuration or from updates to the software stack. It is also good to mention that we are open to publish data from other systems where Easy is deployed. For this, you can contact us on support@easy.io. Now I will take you to Easy Dash and show you the Easy dashboard. So this is the link for the Easy dashboard. Here we can specify the time range. For example, if I want to check the weekly results, and for Easy, and for example, we can go forward and check the OSU collectives. And as you can see, different systems have been reported. Those systems are pushing their data to the Easy dashboard. To get a better view, I can choose some systems. For example, if I choose the Senelius Rome, I can see the different times for the software run and the difference in performance. So as mentioned earlier, this can help system admins to identify things like load on the system or degraded performance. So this can be very, very helpful. I will go back to the slides. Here again, I can see a slide. In this slide, I'm showing a screen from the dashboard where TensorFlow version 2.13.0 was running on Snellius, a supercomputer using different nodes, and I can easily see the performance difference. So this is another use case where the Easy dashboard can give a clear performance visualization for the test suite which we were running. So now we will run into Easy use cases. Now that we have seen what Easy is, how it runs, how to access Easy, Easy has different use cases. One of the core strengths of Easy is its ability to provide a uniform software stack across HPC clusters, cloud platforms, and even personal laptops. So by standardizing software environment through a shared infrastructure, Easy eliminates the inconsistencies that often plague scientific computing across different systems. Whether you're developing code on your laptop, putting it in the cloud, or scaling up on a supercomputer, you get the same reliable, optimized software stack. This consistency also means portable workflows become a reality. Researchers and developers no longer have to rebuild or reconfigure their environments every time they switch to other systems. A workflow built and tested in one environment will just work in another with minimal effort. Beyond researchers, EASY is a powerful tool for HPC training and education. Setting up an environment for a training course can be time-consuming and error-prone, but with EASY, instructors can give students immediate access to a fully configured professional-grade HPC software stack. It's like a plug and play, and it works anywhere. Also, there is a work progress with Open on Demand, where EASY will provide the scientific software, and Open on Demand will provide an easy way to access it. More than that, EASY is a powerful tool for EASY, since it offers a uniform software stack, developers and users can even make use of the CI that is provided through EASY. For this, you can scan the QR code available on screen, and there is a dedicated session on the 26th of May which will cover this issue. And finally, EASY enables strong collaboration between software developers and experts. With everyone working from the same environment, there is less friction and fewer bugs caused by version mismatches or incompatible setups. This accelerates both development and discovery. There is another work in progress in EASY, and that is dev.easy.io CERN VMFS repository. It's now available on Vega, and basically it targets deploying a pre-release version of the scientific software before deploying it into production in EASY. And for more information about this, you can check the easy.io/docs repository/dev.easy.io. So, as a summary, EASY in a nutshell, EASY is an on-demand streaming of optimized scientific software installations. It works on any Linux distribution, thanks to the EASY Compat layer. It's a uniform software stack across various systems, laptops, HPC, cloud, etc. And it's definitely is community-oriented, as we have seen earlier. EASY also won an HPC Wired Reader Choice Award in 2024. You can find more information about this through the link provided under easy.io/doc/blog. And we are happy to receive your emails or via GitLab for any problems, questions, or issues that you're having for installing, using EASY, or even for contributing to EASY. There is also tutorial for best practices for SermVMFS available on the shown link. And also you can scan the QR code as mentioned earlier and attend next week's webinar that is dedicated for SermVMFS usage. Here we can see a comparison between the software stack available from EESSI for the Zen 2 CPU microarchitecture against a locally built software stack for that CPU microarchitecture. And we run 3 tests. The first is using the local software stack. The second is using the generic stack provided by EESSI. And the third is using the stack that is optimized for Zen 2 using EESSI. And as we can see, the results from using the local software stack and comparing to the results from using the Zen 2 that is optimized for the software stack that is optimized for the Zen 2 CPU microarchitecture from EESSI are very, very close. And this test is running on 128 cores per node. Those are some useful links for easy.io, EESSI on GitHub, documentations, and blogs. Also YouTube and EESSI support portal. And finally, it's good to mention that EESSI also is part of the Multi-xCare project, which is co-funded by the European Union and the Euro-HPC joint undertaking. It's a collaboration between 16 partners. It couples the scientific expertise of SECAM network with the technical expertise of the EESSI collaboration. I hope you enjoyed the session and it was very useful. And I will keep the window for Q&As. Thank you.
Thank you very much, Richard. Okay, we've had a couple of questions in the Slack already. Most of those have been answered. But to participants who want to ask a question here, that's definitely also possible. So if you want to speak up and ask the question to Richard or Helena, please raise your hand in Zoom here and we can give you the floor. Or you can also keep asking questions in the Slack for sure. So I see people raising their hands. Eshan, I'll go ahead and give you permission to talk so you can unmute and ask your question.
Thanks, Richard and Helena. A question for deploying EESSI locally, how much storage are we talking about?
Basically, it is, if you want to deploy EESSI locally, it's all based on first, if the client cache size, and second, on what is accessed. So if you are supporting EESSI for different architectures, the client cache will load software for different architectures. But it is not a huge size. The requirement can be around 150 gig. And you can find best practices for this on the multi-xscale.github.io and even on the eeessi.io website.
Sure, thanks. I will check it out. Thank you very much.
It depends on what you exactly mean with your question, Ishan. Like for the client cache, typically, let's say a couple of gigabytes, say 10, 20 gigabytes of local disk is enough for the clients. If you're talking about a full mirror, then today at least we're talking about a couple of 100 gigabytes, but that's for everything we have in EESSI. So all different CPU targets. And we're seeing a rate of growth there in the full EESSI repository of about 1 gigabyte per day, roughly speaking.
Mm-hmm. Yeah, that was my question.
Yeah, we don't really expect to see that increase a lot. So that's more or less what you're looking at. So it's pretty modest actually in HPC terms.
Yes. Thank you very much. Thanks.
Another question, Leon? Go ahead, you can unmute yourself.
Yeah. Sorry, I missed some important questions about the environment itself, so I pretty well understand how does it works, except that I am more concerned in the software that is being built on top of Easy Build and then put into EESSI, which is kind of difficult to pronounce. Let's say kind of easy. It's not that easy to say that. Overall, I wonder how adoption of this easy will be easy for HPC centers to do that, to somehow reduce the burden of sysadmins to provide some of the softwares, and what are, let's say, Euro HPC plans in terms of providing that, considering that a lot of, let's say, competence centers and centers of excellence in HPCs in Euro HPC do not use all the software provided by Easy Build. So this is kind of oftenly custom compilation software that is being built for the scientific software. So it's not that easy to build some software with Easy Build because it lacks a lot of important libraries, and then overall, even those excellence centers of excellence do not provide the Easy Build routine. So I'm interested, how long will this easy last, or when the funding stops, or is there assurance? With Easy Build, you have, let's say, repositories, recipes, and you can do it on your own cluster, optimized in your way, except that it's a burden, while Easy builds this for you. So can you explain about the politics behind the Easy for the European software scientific installations? That actually I don't see any of it except the GROMACS as an example, which is not bad example, I must say. But overall, how long will this last, and how easy will be for the HPC centers of excellence to add their own, let's say, builds into Easy?
Yep.
Does it needs to go through Easy Build? And quite oftenly I see, for example, Lumi is doing their own repo of Easy Build recipes, and they don't even want to go into Easy Build pull requests and so on. So this is, let's say, the question.
There's a lot of questions here, I think.
Yeah, some are comments, but let's say...
Yeah, sure, no problem. So I don't know, Helena or Richard, if you want to answer part of the question, I can definitely pitch in a bit as well. Okay, well, so let's say your question is mainly about politics and uptake and how will that all work. Where through multiscale, Easy is now funded for the development of Easy, let's say, to make sure it's well adopted, to make sure it grows. We're already engaging with several Euro HPC centers of excellence who are interested in making their software available in Easy, so that we see already that's happening. We didn't give very concrete examples here because we want to focus on applications that most people know, like indeed GROMACS. But for example, Espresso and LAMPS, which are two applications that are used in our own Center of Excellence multiscale, are already in there. OpenFOAM is as well, which is also used by some centers of excellence. And we're working together with other centers of excellence who are interested in getting their software also available in EESSI, and by adding it in EESSI, making it easy to run on the various Euro HPC systems as well. So that's already happening. We see this as an ongoing community effort, a bit like Easy Build has always been. In terms of adoption of EESSI itself on Euro HPC systems, that's also already happening for a while now. And that's also being fueled by the fact that EESSI will be used as a federated software stack in the upcoming Euro HPC Federation platform. So that's like a, let's say, a website where people can more easily access the Euro HPC systems. And as a part of that service, there's also a shared software stack, which is actually filled in by EESSI as well. So that's, I think, part of the answer. In terms of politics and how EESSI will keep operating beyond the current funding, we're actively exploring other ways of making sure EESSI is funded. One approach we're considering is setting up some kind of non-profit where we can get sponsorship or funding directly from Euro HPC centers and just general HPC centers in Europe and beyond that as well, to pitch in a bit of the funds that are necessary to keep EESSI developed and maintained going forward. That's one approach we're considering. We're not actively doing that yet. And there's other options as well, like applying for additional Euro HPC funding as well. So that's things that are being explored. You had another question as well in terms of how much sense does it make for, let's say, Center of Excellence to add their software to EESSI, since they prefer doing custom builds or maybe not using Easy Build as a mechanism to get stuff installed. We'll actually have a separate webinar on that topic alone. So using EESSI as a base software stack, in the sense that it can provide you a whole bunch of dependencies and that you purely focus on what you want to build yourself or what you want to configure yourself in a particular way. So we have good ways of doing that as well. We have scripts and documentation to make it as easy as it can be. So it can sort of level the ground across different systems, give you a bunch of dependencies that are good enough to then build your own stuff on top of. And that's a use case we definitely support well as well. And there, that building can be done manually or through Easy Build or through other tools like SPAC as well. We haven't tried that yet, and there's probably a little bit of work to be done to make that use case possible. But it's definitely a use case we want to support going forward as well.
So the route through Easy Build will be supported. I would rather see Easy Build to be more supported in order that hundreds of pull requests are laying and will be most probably abandoned, so that somehow unification of all these Easy Build routines could be comparable to what SPAC is providing. Except that this is more a trial and error, but I don't want to look around over GitHub to find the recipes that nobody wants to merge in just because it's not supported well.
Okay, well, this is this is a two-way street in some sense. It's working together with the community and making sure that the things that they really care about are actually going through. You're raising a good point about pull request in Easy Build, but that's maybe better to discuss in the next webinar, or actually the one on the 19th of May, where we focus on Easy Build itself.
Okay, thank you.
Yeah, if you have any further questions, I think the EESSI Slack is a good place to raise them and have further discussion on all of this.
Yeah, I would rather see some messages from Euro HPC that would be direct to the centers of excellence in order to somehow integrate this Easy Build and EESSI and centers, not on the voluntary basis, but some kind of mandatory.
That's actually sort of happening through the federation platform. Since EESSI is used as a federated software stack, Euro HPC centers are expected to make EESSI available as well. And it's actually happening today already. Yeah. So there is some political pressure and making sure this gets adopted.
Okay, thank you. No further questions.
Okay, thank you. Any other questions? Or Thomas, I don't know if there's any questions we should raise here that were asked in Slack. Is that Does that make sense? I see more questions popping up. We will not raise all of them, of course, but it's good to see that people are also engaging there with the community. That was definitely the goal of recommending people that they raise their questions in Slack. It seems to be working.
There's a question there on licensed software. So in the EESSI Slack, so what we do as regards licensed software, I think that's worth raising in the recording, right? So to give people an idea there.
Okay, well, maybe you can read up the question because I.
Yeah. Are you planning to support also licensed software with EESSI? Of course, with the licenses bought for any HPC center. I mean, I can probably say something about that. So we distribute open source software primarily, right? So we can distribute part of, say, like licensed software, say like CUDA, for example. We can't distribute the compilers, but we can distribute the runtime. And then so we have some tricks around there to, well, we do that, we distribute the runtime, and then we have some tricks to allow you to fill in the gaps. So we have some scripting that allows you to fill in the gaps for the missing binaries on the CUDA installation to give you a full CUDA installation locally. As regards further extending that to other licensed software, that depends on the license. If we can't distribute it, we can't distribute it. But that doesn't mean that you can't have an easy build recipe for that software, right? So it doesn't mean that we can't work together to make sure that we have a recipe that works on top when using EESSI as a base for the software stack. And then we have mechanisms inside EESSI to allow you to extend EESSI. And so you can use that, right? So you can build on top of what EESSI already delivers to provide licensed software.
And maybe if we're a bit more ambitious going beyond that, we could look for agreements with the vendors of this licensed software and see if they are up for allowing us to ship it through EESSI and then bring your own license kind of approach. I think Thomas has a comment.
Yeah, just a little bit to add. So one nice thing with EESSI is that we basically just use the standard EESSI build, EESSI configs. So we don't do any special things to these. Sometimes we have to use a little hook, to maybe adjust them a little bit. But for most of the software we've built and installed, we don't have to do things like that. So that's a very nice thing for anyone to know. So if there's an EESSI build config already available, you can easily try to build that on top of EESSI, install it locally, and then you avoid all these license issues if there would be anything.
And I can also add that on our local HPCs, we were able to build licensed software on top of EESSI. And as mentioned earlier, a session on the 2nd of June is targeting specifically this, using EESSI as the base for a system stack.
Okay, yeah, I think that answers Eduardo's question that was raised in Slack quite well, but we can follow up on that in Slack itself. If there's no attendees in the webinar who have any further questions, I think we're ready to wrap things up. So if nobody raises a hand right now, we'll wrap it up here. Thank you very much to both Helena and Richard for a very interesting webinar. And as you can see here in the slides, there's 4 more webinars coming up in the 4 next Mondays. So if you're interested, please join those as well to learn more about CernVMFS, which is how we distribute the software in EESSI. EESSI Build is how we currently install the software in EESSI, and then 2 specific use cases that EESSI enables. Okay, we'll wrap things up here. Thank you very much, everybody, and see you soon.